The 3rd of June 2025, and we'll just do a little thing here. I've just done a video for people starting off about threads and how you know about threads, and I want to show you a few tools that you use in drilling machines and in lathes for producing holes, generally for drilling and boring. Now a twist drill. A drill is a twist drill. This is a twist drill. The right name of that is a twist drill. It is not a drill bit. It's a twist drill. Now, this is a yoke I bought years ago and never used it. I got it for nothing at Clottermart. He was closing up. He said, I'm going out here, I'm not coming back. And I bought that. Maybe give him 50 cents or something for it. Would you believe what that is? If you want to post what that is. Now, there's a hole up through it. That's tungsten carbide at the top. That's a deep hole drill. That's designed to drill long distances into metal. And some of these will drill are only a 1/4 inch and they'll drill a metre into metal. Can you believe that you can drill a metre? Now, where this comes up big time is in aviation industries. And another place they use them is the crankshafts of engines. They need to drill a straight small hole to bring the oil from one bearing to the next through the journals of the crankshaft. And ordinary drills will not do it good enough. These tend to drill very straight. So you see how it works. Fluid is pumped in here at very high pressure. I don't want this hole. I have no reason for it. I'd love to test it sometime. And it forces out here through the 2 holes. See there? There. And that pressure, it cuts on one side. Do you see the way it's shaped? And that pressure pushes the chips back along this ridge. See here? Pushes it back along here. And when it's running, the fluid comes out here and it'll cut you with the pressure. You have to have a box on the lathe, or the drill is a special drilling machine. You can use a lathe because the pressure of the you use a very high pressure pump. The fluid coming out, even the white fluid, or you can use special lubricant, brown lubricant, it'll hit you and it'll drive it. And when you eventually get out, it'll drive the oil way out, maybe 40 feet or 10 meters, whizzes out there. So this is how it works. The high pressure goes in, it can't get out, it can only come back along here, and so the chips are pushed out here. There's a box here to stop the flow coming out, and it falls down on the bed. And that's a deep hole drill, and that's quite a big one. That one there is about 1 inch. That'd take a good deal of power, and that'd take a very strong hydraulic pump to pump the fluid out of it. But it's a good exercise to see how it's done. Now, they are normally not that big. Normally, they could be 3mm for oil holes. And they can be used anywhere you need an accurate hole. If I were to make a small lathe, I'd probably use this to drill out the mandrel accurately. Now, one of the things that people don't often understand too is, how do they get them so straight? How do they get things so straight? Why does it come out exact? This comes out a lot better than a twist drill that you might weld onto a bar, but it's not exactly straight. And I do apologize, the birds are going mad over here as well, but I want to show you how they do it. Now, this is a bit of hollow bar. You can buy this. And it's very useful for making spacers and washers. You've no drilling. Making special spacers. It's already drilled 1/2 inch. You just get it 1/2 inch. You get it from Impact Steels in Dublin, but they usually only sell it through an agent. So I get it from Moffat's and Tapered. Now, if you're drilling through this with a smaller one, and it comes out a bit off up here, what they do is they turn it down to the right diameter. In other words, this starts off maybe 1.5 inches. They drill it. They then turn it, and that puts the hole up through it concentric with the bore. Do you understand me now? And in a lot of engineering, they do the internal work or the difficult work, and then they shape the outside to suit it. You do not have a big long bar and hope that the thing will come out the right size. Oh my God, oh, that's not the right, it's not in the middle. What are we going to do now? Well, it's not the way to do it. You drill it first, and then you machine it down to be concentric with the bore. Are you with me now? So that's how they get that done. That's how they make big, long, hollow components and that. Now, in a lot of cases with steel pipes for hydraulic oil, they're made in the factory. They're rolled out and they're joined and they're seamless joining. They don't drill a lot of holes for ordinary stuff. It's only where precision is needed. Where precision is needed, where you need it very central. And very often, if a thing was spinning, you need it very central because it'll wobble. So if this were, we'll say this is for a wind turbine shaft coming back to the generator, and that's not perfectly central. When it goes at high speed, it'll wobble. So you need it perfectly concentrical. You need the hole in the center, central with the bearings. Do you get the point? And you can't do that by any means, only by deep hole drilling and that. Deep hole drilling and turning afterwards to the correct size. So you have that. So we've dealt with deep hole drilling. But for most of the workshop, you don't need that. You'll do an ordinary twist drill. Now, in the case of the ordinary twist drill, you usually have the 2 flute, which does for most works. But when you drill a hole, the right way is drill a pilot, and there's a 3 flute. Again, there's a brand new one. That's a very expensive tool. I bought that at the variety market, very little. And those lads at the variety market, they have to make a crust. Look at them, look at that. That there will build, and I have more of them. That'll drill a very good hole. And if you have everything drilled out to near the size, before you start this one, you get a lovely finish with that. But you don't drill from the solid. These will not drill from the solid. Okay, there you have your twist drill types. And some of them have a Morse taper that's a 2 Morse taper. And some of them are straight shanked. That's a 1 Morse taper. We're not going to that. Now the thing is, this is a counterbore. A counterbore bores a hole with a flat bottom. A countersink has an angled bottom. Okay? They're 2 different things. So that's a counterbore. So I use this if I'm drilling down into something. I drill down maybe with a hole slightly less than this in diameter, and then I drill down, and then this will leave place, and you can put your cup head screw or your Allen. I don't have an Allen there anywhere about, but you know what an Allen screw is. They call them cup heads, and they're here on this lathe, but I don't think there's any just there, but it doesn't matter. You can then fit this. This fits the Allen key, the Allen exactly. So when I'm making components, I use this as a counterbore, rather than trying to use a milling cutter, which has no guide. This has a guide. So that's a counterbore. Again, bought at the variety mart for maybe €5. You'd probably pay 50 for it. Keep it safe. Keep it safe, you'll want it sometime. Now, when you have the whole board, the next thing you have is a reamer. And that smooths out the hole and makes it a better hole. So this reamer is tungsten carbide tipped, and I bought that. I think it's a companion for this tool here, as far as I know. And it makes the hole smooth. And but it's tungsten carbide and it got broke. So you just have to be careful with this equipment. They're designed for cutting, light cuts, not for driving in, horsing them in. This is a proper tungsten carbide reamer. And it's Morse taper, it's 3 Morse taper. So that'll only use in the head of my lathe, because my tailstock is 2 Morse taper. And really, except for small lathes, I think 3 Morse taper is the way to go. So that's a reamer. Now, so this is a high-speed steel reamer, and some of the men for model engineering make them out of silver steel on a lathe. They cut the flutes straight. Now, these have a twist. Sorry about that. Some of the reamers have straight flutes instead of twist. So if you look at this one here, it has a negative twist. It tends to push the chips forward, whereas this twist drill has a positive twist. It tends to root out the metal up along the flutes. Getting rid of all this metal is important. And with a drill like this, you have a lot of metal to get rid of. Whereas this one here, you have to pull out the metal. The reamer has an existing hole and it pushes it inwards. Do you understand? So that's a negative twist. So it's the opposite direction. Now, you can have a straight one. You can have one with a straight flute, and they work quite good too. And you can make them yourself. Now, here is another reamer. This is a Morse taper reamer, and this is designed to widen out a Morse taper that's a bit damaged and clean it up. Again, bought at the Variety Mart. You'd pay big money for that. I got that for very little. So you can give your Morse taper a little clean, but you must remember you could change its throughness. So a lathe, for example, the Morse taper is normally supplied through to the mandrel and the bed, and you've got to be very careful. You can give it a wee clip, a wee bit, and not so much. And that's why it's important to drive in your Morse tapers right and not have them spinning. This part here, on the blade mandrel, there's nothing to grip this. They're taken out by twisting the wheel backwards, and it pushes it out. On the drill press, people think this is a gripper, but actually they're meant to be held by friction. And on the milling machine, on a good milling machine, there's a bar going down through the milling machine quill that pulls it up. When you put it in, you tighten the bar on the top, the drawbar, and you pull it up. And that means there's no slip. That's the disadvantage of the Morse taper for a lot of work. There's no thing holding them into place. Whereas if you buy a collet chuck, you will get this type of arrangement, but you'll have a drawbar to go through the mandrel of the lathe and pull it in, and so you have a much better joint. That's it, folks. I have to go on a domestic thing. Now, I have made reamers out of, I don't think they're here. So what I do is I get a piece of brass bar. I mill a slot along here. I put it in the tool post exactly right with the mandrel, and I mill a slot right across here with a slot drill or a woodruff miller. Now, we're not going to deal much with milling here, we're dealing with drilling. But I cut a slot. I then get a hardened high-speed steel bit that fits exactly in there. I don't know where to ever find it. It's here somewhere. I'll probably not find it now, but it's sitting in this slot. Now, I put a wee bolt there that it can't pull out, and I put the high-speed steel in, and I measured with the micrometer till I get it the same across. I then grind a nice little slope up like that on the piece of square section. High-speed steel, and I grind the advanced part of it a bit more, like I grind the advanced part so that it's sloping in, and the following base is a wee bit behind it, so that it's the front section cuts. Now, I'd love to, might actually do one on this, but I'll give you an example of how it works. Now, just a second. I have good jumper on me. I have to apologise, I should have had a dirty jumper. It's a terrible thing for an engineer to have a clean jumper. I didn't buy an apron yet. You know, I might. Now, this is the idea for the reamer, for the reamer. You see? That fits into the slot. You then grind off this edge, and you have this one a little bit behind this one, so this one does the cutting. Now, here's the thing about that. This first part cuts. I'll show it to you this way. This first part here cuts. The back part burnishes. It burnishes. In other words, it improves the surface. And these are called a spill. S-P-I-L-L. And I have done some lovely surfaces with them. They're single point. And instead of pushing it through, it's what you pull it through. Now, you have to get some way to get lubricant into it. Some way, or you put some arrangement on the top with a rubber ring or something that'll push the lubricant out. Good old lubricant. You can buy the lubricant too, even something better than the white fluid. You know, the white detergent type water-based stuff. So this is a spill. And this was used long ago when they needed to produce a long hole. So you have this here like this, and you're pulling it out through the thing. Now, you bring it down till it's almost level. This bar here would be a nearly tight fit for the hole, but not a tight fit. This here will be a little below. And you bring this up by very slight pieces of paper, cornflakes box, or even cellophane off a cigarette packet, or it used to be long ago, whatever. You bring it up very slightly. You pull it through. You get nothing the first time. You pull it through the second time on the lathe, and you see little chips developing on it. When you see the little chips, you give it another wee raise and you pull it again. And then as you go to pull it, it produces a perfectly straight hole. Now, it's not entirely perfect because this is guided by the hole at the bottom. And no one has ever managed to get away to drill a perfectly straight hole. And in a lot of the works, they had a straightener who viewed the thing up through the a window, and there was a line hanging down, a piece of cord or black wire, and he viewed it through it, and he could know by the shining how straight it was. And there was a machine then for bending it slightly. But generally speaking, for most works, and like doing a wind turbine now, and I'm not big into them yokes, but doing a shaft where the hole has to be definitely central and it's running at high speed, you need it perfect. So I just want to show you that you've heard that word. I bet you never heard the word spill before. And in olden times, they used to use blocks of wood underneath here. Now I put you a wee bit wrong there. That's my way of doing a reamer, a homemade job where time is not an issue. But in the works long ago, before they had reamers, they used a spill, and the spill had this section. Do you see that? It was hardened and tempered. It was ground on all sides. All sides. And there was wooden, I think it's the wood that was called the spill. Somebody might know. But the wood would go underneath it here to force it up against the hole. And as it drilled and reamed out, as it reamed the hole, more spacers were needed. So they made this a tight fit, and they put a wooden thing with a mortise out of it here to keep it up against it. And then this could go around, or the work could go around, and the wood kept it tight up against it. And the way it was, this now, I wonder could I show it to you here? So this here, this is just all I have available. This would be a tight fit. Now, this would go round, or this would go round, and there'd be a piece of wood. See where my finger is here? See my finger? Look at a piece of wood here. And they'd keep putting little pieces of paper or whatever behind this piece of wood. The wood had fit round this, so they had pushed this up against it. There'd be a relief cut on the front, a gradual spin on both sides, the way I do it, a little bit less on more on the leading end than on the following end. And so this would be forced up against it, and they'd pull this through. And as they pulled it through, they tended to make the hole straighter, because you're pulling. You know, if you're trying to pull a piece of string, it's easier than push it. So this pulled it up, and the first cut here, do you see the leading edge up here? See this cut and this burnished. So what you got was, I'll put it here where you can see without my shadow. You got the leading edge cutting, and you got the following edge burnishing. Do you see that? And that gave them the surface they want. They got cutting, and they got burnishing, because the angle here is aggressive. The angle on the top here is aggressive. Do you see? Whereas the angle here is not, well, I don't think it's quite as aggressive. It's not the same. Do you see the angle? This will cut, this one, do you see? So we'll just look at that here. So this tends to cut because it's aggressive. It's at an angle that's more aggressive, where this is at a lesser angle. And this burnishes it, given a finer hole. Right, folks. There was great ways of working along. I'm fascinated by how they got things done and how they made the old mills and all that. But where this really comes into its own, where you had to drill a shaft that had to go through, and there had to be something put through it. Even the steering column of an old car, the driver was twisting around. There had to go wires down through it. That had to be concentric. And so you had to have a way to drill it. And then when you had it drilled, you had to make it central. And I've let you in on the secret. The secret was you turned it down in the lathe to make it concentric. When you got it close to concentric, then there was a fella to make sure that it was straight. And he done that by putting it up against a window, usually a northern facing window, and he got it straight, depending on the application. A steering of a car could be out a bit. But if it was spinning around at high speed, it had to be fairly central. And if it was an engine component, it had to be perfectly central. You couldn't have it wobbling like this, otherwise you'd have a shiver. So these things all come into play. So what you did was you drilled it, You then reamed it with your reamer. Nowadays they use a pull reamer. They use a reamer like this one here. Have I one here? What do I do with it? Yeah, they use one like this. But instead of pushing this in, they pull it. They pull it through and it's lubricated. So when you pull, you tend to get a straightening. Do you know you have a pull out of it? And then when they had that done then, and a nice shiny surface, they straightened it and then they turned it again and they take a little cut till they got it perfect. If it was vital, they'd have it perfect. They'd make sure it was as straight as could be on the inside. See that? As straight as could be on the inside. And then when that was, everyone was happy, they turn the outside of it, and then they might lap the surface with a lead lap if there was something to move up and down in that, but it was only fluid they wouldn't need. Whereas a lap could put a slightly better surface. So that's how they did, is how some of these great things were done and how they were made, and it was a credit to them, I mean, how they did it and all of that. You can imagine a horse-pulled threshing mill, if you had an imbalance in the drum going round, the poor old horse would find this bzzz going round, whereas if you had everything perfect, it was just more smooth. Comment underneath, we'll see you back. I know this is not for everybody, but sure, look, I want to talk about all things. Good luck, thank you.